Hi, I'm Adrian Agtalao and this is a presentation about special purpose diodes highlighting on Zener diodes. And I am together with my partner Patrick Watson.
Special purpose diodes.
There are different kinds of special diodes. These include Zener diodes, LEDs, photodiode, varactor diode, tunnel diode, Scotch-K diode, Scotch-K diode. The Zener diode is a silicon p-n junction device that differs from rectifier diodes because it is designed for operation in the reverse breakdown region. The breakdown voltage of a Zener diode is set by carefully controlling the level during manufacture. The basic function of Zener diode is to maintain a specific voltage across its terminals within given limits of line or load charge. Typically, it is used for providing a stable reference voltage for use in power supplies and other equipment. A Zener diode is much like a normal diode, the exception being that it is placed in the circuit in reverse bias and operates in reverse breakdown. This typical characteristic curve illustrates the operating range for a Zener. Note that its forward characteristics are just like a normal diode. Zener diodes are designed to operate in reverse breakdown. Two types of reverse breakdown in a Zener diode are avalanche and Zener. The avalanche breakdown occurs in both rectifier and Zener diodes at a sufficiently high reverse voltage. Zener breakdown occurs in a Zener diode at low reverse voltages. A Zener diode is heavily doped to reduce breakdown voltage. This causes a very thin depletion region. As a result, an intense electric field exists within the depletion region. Near the Zener breakdown voltage, the field is intense enough to pull electrons from their valence bands and create current. The Zener diode's breakdown characteristics are determined by the doping process. Low-voltage Zeners less than 5 volts operate in the Zener breakdown range. Those designed to operate more than 5 volts operate mostly in avalanche breakdown range. Zeners are commercially available with voltage breakdowns of 1.8 volts to 200 volts. Figure shows the reverse portion of a Zener diode's characteristic curve. As the reverse voltage VR is increased, the reverse current IR remains extremely small up to the knee of the curve. The reverse current is also called the Zener current, IZ. At this point, the breakdown effect begins. The internal Zener resistance, also called Zener impedance, ZZ, begins to decrease as reverse current increases rapidly. Figure B represents the practical model of a Zener diode, where the Zener impedance ZZ is included. Since the actual voltage curve is not ideally vertical, change in Zener current produces a small change in Zener voltage, as illustrated in figure C over here. Example 1. A Zener diode exhibits a certain change in Vz for a certain change on Iz on a portion of the linear characteristic curve between Izk and Izm as illustrated in the figure. What is the Zener impedance?
So here is a given formula to answer the question. First, we need to look at the graph to see what values to replace the variables in the formula with. So delta Vz and delta I2 are replaced with, for delta Vz, we have 50 millivolts, and for the change in the current, we have 5 milliamps. We replace this into the equation, and we have the following. This unit crosses out. We now have 50 over 5. 50 over 5 equals 10. And the unit for this will be ohms. A certain Zener diode has a maximum power rating of 400 at 50 degrees centigrade and a derating factor of 3.2. Determine the maximum power the Zener can dissipate at the temperature of 90 degrees centigrade. So the formula given is PD derated equals PD max minus MW over degrees centigrade times the change in temperature. So we substitute in the values from the problem. So PD max, that equals 400. Then MW over degrees centigrade, that's also given in the problem as 3.2. Change in temperature. Since in the problem it says the Zener can dissipate at a temperature of 90 degrees and the maximum power rating is at 50 degrees, we have our change in temperature to be 90 degrees minus 50 degrees. And now all we have to do is simplify. So bring this down. Ninety minus 50 is 40. And that becomes and 400 minus 128 is 272, and there's your volume.
Now, I'm going to explain more about Zener diodes. This is the symbol for a regular diode, in this case a silicon diode, and this is a symbol for a Zener diode. We have to be careful about this because they behave differently and they don't have the same use. With a regular diode, current can only flow in one direction. But for a Zener diode, it can actually allow current to flow in both directions. Think of Zener diodes as two regular diodes in parallel facing in opposite directions and each with different voltage drop. When current is being pushed this way through the Zener diode, there is a forward voltage drop that is usually around 1 volt. The diode will not even allow the current to flow unless you have at least 1 volt. When the Zener is in forward direction, we can say that it is forward biased. But going the other way, there is a different voltage drop called the Zener voltage, or VZ. In this example, it is 3.3 volts. This Zener diode will not allow current to flow in this direction unless there is at least 3.3 volts across it. It is like the forward bias that I have shown a while ago. But when there is sufficient voltage, current can now flow in this direction and will have a constant voltage drop of 3.3 V or 3.3 volts. Since current is flowing backwards, we can say that the Zener diode is in reverse bias. This property of having predictable voltage drop is what makes Zener diodes useful. If you set your circuit up just right, you can use Zener diodes to limit the voltage.